Hi everybody, in this video I'm going to talk about electromagnetism and devices. So this is part of the APEX study section 9.3.3. A quick word about that study section. So that study section is pretty long, it has a lot of topics in it, so I wanted to break it down into more manageable pieces. So we already did part of this study section when we did the PhET simulation and when you did the first right-hand rule and the demo in Edpuzzle. So that was the first part of 9.3.3. This is going to be the second part where we talk about electromagnetism and how it is used in devices. And then there's going to be a third video on a second right-hand rule and Lorenz's law. Okay, so I just wanted to break that down and explain what I was doing. All right, so let's take a look at this electromagnetism and devices. We know that electricity and magnetism are related. This is very clear in an electromagnetic wave. You know electromagnetic waves as light. Light is made up of electromagnetic waves. In an electromagnetic wave, we have an electric field, which here we have represented in blue, and a magnetic field, which we have represented in red, and they are traveling perpendicular to each other. That means there's a 90-degree angle between the electric field and the magnetic field. They are oscillating back and forth as that wave propagates, as that wave continues. It's kind of hard to imagine, so I have a graphic here. So again, we can see the electric field represented in this one as red, and it is oscillating up and down. We see the magnetic field, which we also call the B fields, in blue, and it's oscillating back and forth. And you can see that they are at a right angle. So this is what an electromagnetic wave looks like. It is these changing electric and magnetic fields, and this is what light is made of. Okay. So another thing we know, what we have learned from our PhET simulation, is that if we have a loop of a current-carrying wire, it can create a magnetic field. So if you have a wire that's carrying current in a loop or a coil, it creates this magnetic field. And when that happens, we call this an electromagnet. When an electromagnet has more loops, it creates a stronger magnetic field. If it has less loops, it would be a weaker magnetic field. This also works in the other direction. If you have a loop of wire with no battery, no voltage source, you can put a changing magnetic field through that coil or loop of wire, and it will induce a current. It will create a current within that loop of wire without a voltage source like a battery. And again, in this case too, more loops means more current is induced. So let's look at an example of this. All right, so here we have this coil of wire, and you can see that it is not hooked up to a battery. There is no voltage source. But if we just bring this magnet closer and further away, we have a changing magnetic field. You can see that a voltage is produced. And if we increase the number of coils, you can see that voltage is induced as well, and it is a greater voltage. Right here it's going about to 20 volts, whereas in the smaller one, it's only going not even to 10. Okay? You should also notice that if the magnet is right next to the coil, but it is not moving, that does not induce a current. It needs to be a changing magnetic field. That means something needs to be moving. And that's what we should have seen in our PhET simulation. If it's just next to a coil, it's not going to induce a magnetic field. It needs to be physically moving. Okay. So, now there are a lot of devices in our lives that use induction. 3 of them that we're going to talk about are motors, generators, and transformers. So first we want to talk about a motor. A motor is something that can convert electric potential energy into mechanical, or we call it kinetic energy. So what happens is a motor contains a voltage source like a battery, and it's connected to a loop of wire. And we also have a permanent magnet. So when the voltage source is turned on, current starts flowing through the loop of wire, and we know that creates that electromagnet. The electromagnet interacts, it attracts and repels with the permanent magnet, and that causes it to rotate. And then you can connect something to that rotating wire to make it move. So let's look at an example of that. Okay. Looking over here, we have a battery. Our battery is represented here. And it's connected to a loop of wire. And that loop of wire has a current through it, and that current creates an electromagnet which interacts with this magnetic field. So let's pause it for a second to see how this is happening. Let's get a little further here. There we go. Okay, so here we can see that the current is moving in this direction. I'm representing I for current. Then if you use your right-hand rule, you will see that a magnetic field is induced through this coil with the north on this side and the south on this side. But then we see the north side is next to the other north side, and the south side is next to the other south side. So it's going to repel. So this north side is going to move over here, and the south side is going to move over like this. And that's what's going to cause it to rotate. We have this battery which produces this current through the loop. That makes an electromagnet. That electromagnetic field is repelling the other magnetic field created by this permanent magnet, and that's what causes it to turn. And then we could connect something to this and that thing would turn too. So that's how a motor works. A generator is sort of like the opposite of a motor. What it does is it takes kinetic energy and it turns it into electric potential energy. So in a generator, we have some object that causes a coil of wire to rotate. This coil of wire is not connected to a voltage source like a battery. It's just rotating in a magnetic field. However, since the wire is moving in a magnetic field, it experiences a change in the magnetic field, so a current is induced in the wire. So let's take a look at that. All right, so here, I know this looks very similar, but I want you to notice here that there is no battery. There is no voltage source in this loop of wire. We have some external object causing this to rotate. And we talked about there's a lot of different sources of energy that could cause this to rotate. It could be a windmill. It could be some sort of fossil fuel that is being burned, and then that is causing it to rotate. But we have some external object causing this loop of wire to rotate. When the loop of wire rotates in that magnetic field, it experiences a change in magnetic field. So the loop of wire moves in a magnetic field. I'm calling this a B field. That is how we abbreviate it. As a result, it experiences a change in the magnetic field, and that causes a current to be induced. So there was no battery, no voltage source. We just turned a loop of wire in a magnetic field. And so since it has a changing magnetic field, it induces a current in that wire. And then we can use that current as electricity. Okay, so this is how a generator works. The last thing I want to talk about is a transformer. So electricity is produced in a power plant by a generator, and it is carried in wires to your home. Those are the wires you see outside. It's most efficient to transport this electricity at high voltages. So the electricity in the wires that you see outside is high voltage. However, you can't use that high voltage in your house. It would be too dangerous. So you need a lower voltage in your home. A transformer is a device that we use for this purpose. It can change the voltage. So a step-up transformer increases the voltage, and a step-down transformer decreases the voltage. So how this works is it uses the principle of when there's more turns, more coils in an electromagnet, there is a greater voltage. So let's look at a picture of this. So this first example is a step-down transformer. That means the voltage decreases. And you can notice that in both of these cases, we have this metal core, which looks like a loop, and it has coils of wire on either end. In our step-down transformer, the first coil has more turns than our second coil. That means the voltage is higher before the primary source, where the voltage is coming from is higher, and when it is leaving, the secondary voltage is smaller. A step-up transformer is the opposite. You can see that the first coil has less than the second coil. That means that the primary voltage coming in is lower than the secondary voltage coming out, okay? So the voltage increases. So this is how transformers work. It's a little more complicated, the details of how exactly that changes the voltage, but this is all I want you to know is how to relate that to the number of coils, okay? So in this, we've talked about these three things that we use: motors, generators, and transformers. And we also talked about electromagnetic waves. So again, we've been through most of 9.3.3, and there's going to be one more video about the Lorentz force equation and the second right-hand rule. Please let me know if you have any questions. Thank you.